For example number 12, we want to show how to approximate the required work by a Riemann sum, then express the work as an integral and evaluate it. So in exercise 11 through 18, n is the number of subintervals of length delta x, and x subscript I asterisk is a sample point in the ith interval. In example 12, it says a chain lying on the ground is 10 meters long and its mass is 80 kilograms. How much work is required to raise one end of the chain to a height of 6 meters? So for step 1, after lifting, the chain is a L-shaped with 4 meters of the chain lying on the ground. Now step 2, the chain slides effortlessly and without friction. Step 3, the weight density is going to be 80 kilograms divided by 10 meters, which becomes 8 kilograms per meters, times gravity, which is 9.8 meters per second squared. And that's going to equal 78.4 newtons per meter. Now for part 4, it says part of the chain x meters from the lifted end is raised 6 minus x meters. Now if we know that x has to be in between 0 and 6, and it is lifted 0 meters if x is greater than 6 meters. So the work is going to be the Riemann sum, which is the limit as n approaches infinity of I is equal to 1 to n of the function 6 minus x subscript I times 78.4, which is the weight density, times delta x. So now we're going to evaluate this integral going from 0 to 6 of 6 minus x times 78.4 dx. So if we factor out 78.4 and find the antiderivative of 6 minus x, which is 6x minus 1/2 x squared, and then evaluate it according to the lower limit of 0 and an upper limit of 6. Now plugging in 0 is going to give us 0, so we're going to plug in the value of 6. So we're going to have 6 times 6 minus 1/2 of 6 squared, and then multiply that by 78.4. And we get 18 times 78.4, which gives us 1,411.2 joules, which is how much work would be required to raise one end of the chain to a height of 6 meters.